so today I think it's going to be a short class because I'm going to wrap up Shor's algorithm. So basically we covered the circuit, and what I want to talk about is the computational problem. So as I said, every quantum algorithm consists of computational problem and quantum circuit. So we talked about the quantum circuit. So what is the problem? So it's not really about RSA encryption, but this is the place where the Shor's algorithm are very supposedly have a largest effect. So if it's not about RSA encryption, people will not care about this factorizations and periodic findings. So some of us probably know about this. I'll talk about briefly what's going on. So this is also about two persons. Of course, there is a eavesdropper called Eve, but basically it's about two persons. So mostly in computer science, they call it Alice and Bob. So we have to be careful that who is the receiver, who is the sender. So basically, the Bob is the sender. What does Bob send? Bob sends message. So the message is the packet. Then Alice is the receiver. So Bob wants to send something, but if Bob sent directly to Alice without encryption, then there would be an eavesdropper called Eve. And hijack all the message, right? So we don't want that. So we want to encrypt the message. So how do we encrypt? So I'm going to just give you the outline and then detail and then give the theoretical background. So Alice prepares the key. So it's a public key. And then what I mean by public is that this key is really public. Anyone can see it. So even Eve can see this public key that Alice published. So Alice just say everyone that this is my key. So this mu and e are integers, and mu are supposedly the big integer, and e is something is given according to what the mu is. So, but not just public key. Alice gives the private key. So let's call it D. So private key is secret. Alice doesn't open it, so nobody knows. Okay? And what does Bob do is he prepares a message. Let's call the message, mu. And then he encrypts the message into C. So what Bob sends to Alice is the C. Okay? And then Alice receiving C, which of course cannot know what that is because it's encrypted. If you convert it into string or character, it have no meaning. But she uses the private key to convert it into the original message that Bob prepares, and so only Alice supposedly know what Bob sent to Alice. Even so, here the situation is it's not about quantum channel. So we talked about BB89, which is a quantum encryption, and that is when you send the quantum message, quantum information directly to one person to another, and even in that case, even if Eve knows what this message is about, because of the quantum no cloning theory and some properties of quantum situation, So Eve cannot know what that is. But here, this is not about quantum channel, quantum information. It's just classical information bits and through the classical channels. Okay, so even if Eve know what that is, Eve can just copy the message and then send to Alice. That Alice doesn't know whether this Eve is listening to the channel or not. So how does it work? So first of all, so again, Bob is the sender, but Eve has to prepare to receive. So the process starts from the Alice. So Alice prepares number mu, which is the product of two large primes. Okay, so it's not the same prime, but anyway, so it's so big, only Alice can know what it is. And also, if you multiply two big numbers, then it looks like a prime, but you don't know unless you get to the factor as big as one of the smallest number in between P and Q in order to find out that this is the multiple of two factors, two large factor primes. And also, so that's the first step. And what you do is a public key, right? So Alice finds an integer E such that it's co-prime to n. So here n is p minus 1, q minus 1. So Alice know what p and q, of course. So Alice know the p minus 1 and q minus 1. Therefore, Alice has the upper hand to factor out this large number n. So mu and n is still a very large number. So when somebody just know without factorization, without information of p and q, just if they know what mu and n is, then they have no idea how to factor it out. But since Alice know that it is a multiple of p minus q and p minus 1 and q minus 1, she can easily find some co-prime number. So it can be any random number, but not too small, because if E is too small, the public key is too small, then it's kind of given the wrong idea. But it could be also a big number, so that it's co-prime to this number. What co-prime means is that it has no common divisor. So no common factor in between these n and E. And Alice has to put, so now he prepared the public key. And the next step is to find the private key. So Alice finds an integer D such that when you multiply D and E, it is 1 modulo n. So what I mean by modulo is that when you divide out by that number n, then the remainder is 1. So in the computer language, usually it is this operation is denoted by percentage sign, right? So it's also easy. So it's also depends on the number theoretic fact that if the number is co-prime to this number, then you can always find its inverse, which means that the inverse means that when you think about the number system modulo some number, then this means that if you multiply these two numbers, it becomes identity, the identity of multiplication. So you can say that E and D are inverse each other in a multiplication system of the modulo system. Okay, so that's Alice. So Alice did her job, and Bob now prepares the message. So when you think about, I probably heard about this, when you log into banking system, that you have to update your, what is it, some kind of credential file. So when they do that, they often come with the RSA dash 128, 256, 515, 5512. So that kind of number is number of bits that use for a single packet to transfer one information to another. So usually that number, 2 to the 5, so 512 doesn't mean that it's a 512 bits. It's actually 2 to the power of 512, so it's a very large number. So in that case, Alice in that case is whoever the receiver is publishing the key, the public and private key, in the in the number less than 2 to the 512. It's a very large number, so you cannot really do the factorization by hand or by computer or any classical computer. But so let's go back to that later. Anyway, Bob prepares the message mu, and the mu is supposed to be smaller than the nu, because this nu is already public, so everyone knows that. So if the message itself is bigger than this, which means that, okay, I need to send a large number of strings, then you can just chop up the strings into the tokens so that each token is smaller than this. And Bob encrypts the message to C by C is mu to the power of the, what's the public? E modulo mu. So only mu is known, only E is known. So anyone can encrypt the message, right? So Bob encrypts the message. So there's nothing special to Bob. And then Bob sends it. To Alice, and Alice decrypts the original message by taking C to the power of V, which is actually equal to mu modulo nu. So you see, when Bob encrypts the message, he uses the public key E, and when Alice decrypts the message, she uses the private key D. But even if they didn't use the same key, they can get to the original message that Bob sent, the mu, right? So that's the procedure. So have anyone heard about this? Right? I mean, anyone heard about this before? No? Okay. So let's talk about the underlying problem here. So it's a theorem called the Fermat's Little theorem. There are lots of Fermat's theorems. The most famous one, Fermat's theorem, is the one that you learn in the calculus. Probably not by the name of Fermat, but you probably know what it is if you hear what it is. But this little theorem is about the number theory, and there's a even more famous theorem called Fermat's last theorem, and this is really about the number theory. So this little theorem says that, so if you have a prime number and any integer, the following identity holds for any A that is non So, of course, if a is 0, it never becomes 1, right? So that's why we exclude the case when a goes to 0. So when I say 0, it's modulo 0. So it could be really 0 integer, or it could be a multiple of p. So in any case, if a is multiple of p, if you take the power of multiple of p, it's also, the remainder is 0 when you divide it by p. So we exclude that case. Once you exclude the case, then this is always true. So let's see some example. So well, not the simplest, but let's say the 5, p is 5, and let's say a, so the trivial case is a equals to 1, right? So the power of 1 is always 1. So let's call it 2. So let's say 2, the equation says 2 to the power of 4 is modulo 1, right? So the actual power is 16. So this is 15 plus 1. So therefore it's equal to 1 when you multiply by 5. When you divide by 5, the remainder is 1, right? So that's how it's done, but I want to say a little bit more. What happens is, let's say I want to think about 2 to the powers in a sequel by increasing the powers. So 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, and 2 to the 4, and 2 to the 5, 2 to the 6. So you can go forever. And let's think about the modulo by 5, this modulo 5. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. So far it's just the same number, but now you have to take the modulo from then. 8, right? So it's 3, 16, 1, right? So we come back to 1, and what's the next modulo? So you're multiplying 2 to 1, right? So it's same as you get the 2 to the first. So multiplying 2 from 1, so you get 2. So think about 32, right? 32 modulo 5 is 2. So you don't even have to take the powers. So once you get to the 1, you can just repeat the previous sequence. So you can see that this is the periodic sequence. So when you take the powers, each powers, then you get the periodic sequence. And what's, so 2 to the 6 is going to be 4, so on. So think about the step 5 and 6. Why does it make sense? So we had C to the D, that's the Alice strategy, and that is equals to, well, at least modulo equals to mu E, the power of D. So C is not equal to the mu to the power of E. It's modulo. It's after you take the division by mu, you get the same remainder. So then let's think about mu to the, so this is equals to mu to the DE. And how did you find DE? So DE is our integers satisfying this equation. So in other words, DE is 1 plus n times some integer k. Okay, so let's plug that in. So n is p minus 1 times q minus 1. So we have mu to the power 1 plus p minus 1, q minus 1, k. Right? So I can take out mu, because there's 1 in the exponent. And I have mu p minus 1, q minus 1, k. Right? So now, if I have to prove this, I have to be a little bit careful about this argument. But what I want is, at the end, I want to take the modulo mu, which is p times q. Right? So whatever happens for p and q will happen the same. So when I take the modulo p, then I know that the p to the power of p minus 1 is going to be 1. So what I'm doing here is I'm assuming that Bob is not preparing its message, the original message mu, as a multiple of nu, public key. And I mean, I'm just ruling out all the possibilities that things go wrong. But this is a very rare chance that Bob prepares a message and like among these 2 to the 512 numbers, you get that specific number, but that's not only one, but there is only a tiny number of elements, that number of in between 0 and 2 to the 512 that it has a multiple of mu. So we assume that mu is not multiple of mu, and it almost never happens. So we know that this is going to be modulo 1 when you take modulo p, and also when you take the modulo q, then you can switch the order of this exponent. So whatever that is, anyway, so whatever that is, when you take the power of q minus 1 by the Fermat-Little theorem, that it goes to 0, 1, so on, 1. So in any case, these becomes 1. So what left is just mu alone when you take the modulo of p times q, right? So that's the idea of why the Alice can decrypt the message Bob sent. So here's another important theorem, the underlying theorem. So one is the Fermat-Little theorem. And, so what's the strategy of Eve? So we don't need decryption encryption if there is no eavesdropper. So everything is because there is Eve. So Eve is a very important person. So we don't want the Eve, but if Eve is not there, then the whole theory has no meaning, right? So what is the strategy of Eve? Eve can hijack all the message, and she knows all the public key, but not the private key. So Eve wants to become an Alice. So Eve wants to know what Alice wants. Alice knows. So all Alice knows is the private key D. So how did Alice find out the D? She found out because she knows the factorization of mu. Because she knows the factorization of mu, she can find what n is, p minus 1 times q minus 1. So that's the only reason why she can find the private key D easily, and also find out E as a coprime of that number. So strategy. So we have to argue about what's the best shot of Eve. And so there is only one. Eve must find out what? Eve must find out the P and Q, the factors of n, no, not n, mu. So why is that? So first of all, have you watched the movie? What's it called? So it's a movie about Enigma. When the Turing machine, like I forgot the name of the movie title. So anyone? Imitation Game. Yes. Have anyone watched the Imitation Game? So the way they found the encryption decryption method, or the private key, is to decrypt the message one by one, and then do it until they find the message that it makes sense. So in the German words like hello. Okay? So if that's the case, then Eve can just do the trial and error. So just take a large powers until they get the meaningful message here. But if the message itself is some or a random number or random strings, which is actually another code that breaks another code. So if the situation doesn't allow you to read the meaningful sentence from the decryption, then Eve cannot just try and error, or if Eve have only one shot or finite shots to test out whether she got the right message or decrypted message, then she cannot do the try and error, right? So, Eve, what Eve can do is to find the information that Alice have as much as possible. So that's only message, only information, P and Q. So Alice doesn't have any other information to encrypt the message. And now here's the question. In the perspective of Alice, what's the expectation? So if the factorization is too easy for Eve, then Alice have no guarantee that this message transmission is secure, right? So when Alice is preparing her public key and private key, and when Bob sends a message, they are assuming that even if E listens all the information that we are transmitting each other, the factorization, the best strategy that Eve can do is very hard thing to do. It's not impossible job, but it's very hard. So assumption here, and this is very important and interesting question that everyone, even mathematicians, try to find. The factorization of a large number is hard. Well, it's not a mathematical statement, right? What do you mean by hard? So it's not at all provable by mathematical argument, but people can kind of believe that there's no genuine algorithm that finds a factorization other than just brute force. So what is the brute force? Brute force factorization is known in ancient times, like in BC, some 500 or something, when Euclid was there. So, so what I mean by this assumption is there is, so supposedly, no better algorithm to find a factorization of a number then, so if there's a name, I forgot the spelling, be careful. The sieve of Eratosthenes. Sieve of Eratosthenes. In Korean, Eratosthenes che. So sieve means che. So che means it's filtering something. So it's the thing that you use when you cook to filter water or something. So how does it work? So this is very old. So this is a Greek mathematician, very old, ancient mathematicians, and people never found that. Didn't find a better algorithm than this. So basically, the computational complexity is not better than this one. So you take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you do it again. Just lay out all the numbers that you can think of. And then, whenever you meet the prime factor, let's say 1 is not it, we rule out. So 2 is the first prime number you encountered. Then you rule out all the multiple of that new encountered primes. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 12, 20. Okay. So and then after ruling out of these numbers, you find the next number. So that's the prime number because this has to be the prime number. Then you rule out the multiple of these numbers. So 9, 12, 15, and so on, 18. Right? So and then you go to the next number, which must be prime. Right? So and then you rule out all the numbers here. Okay. 15 here. So this way you can kind of know that what is prime, and you can try out whether your number is ruled out along the way. So you can do this for a fairly large number because of the computer now, but if you have the number almost large as 2 to the 500 powers, then it's very, very hard task, right? So you cannot just do the factorization. And what's the worst case that you can think of that factorization happens? That's the mu, because it's the multiple of two large primes. If you have a 2 times or 3 times in the factor of mu, then you can easily find the factors and then make it number smaller and smaller, one by one. But until you find the number smaller than P or Q, then you have no idea whether this will happen, when will be in N. But I'm saying that this factorization of large number is not possible. It is possible if you have a large amount of time. So that's why you have to renew your certificate file every 1 year. Because when they make a encryption, they kind of assuming this kind of thing, like their standard is something like, if you use this much bits in the encryption, then if we use all the computer powers in the entire globe to work on breaking this encryption, it will take about 3 years. Then they make a certificate, the lifespan of certificate to be like 1 year. So to be safe, because you could be lucky to find out before. I mean, it's only for our personal use. So nobody will just do that only to break our banking system to find out what it is, how much money in our bank, and use all the computer powers in the globe. But it's just to be safe, they kind of standardize that kind of a lifespan of the certificate. That's the idea. The whole assumption is based on the belief that factorization is hard. And what's sure, and so you know that why people are really enthusiastic about the one Shor announced his quantum algorithm, because so at first Shor did not think about this factorization. So I saw the YouTube video that Shor himself is explaining about the history of this Shor's algorithm, and he said he didn't intended to think about trying to solve the RSA encryption or factorization. He just wanted to think about the pattern, how to use the quantum algorithm to find out some pattern. And then gradually people thought that when Shor published his work, people thought this could be used as factorization. How? So that's the next step. Because remember the sequence goes periodic. So in order to find the factors P and Q, what Eve can do is try to make a function f of r, which is x times r modulo mu. Right? So this is periodic function. Why? Because if R, first of all, if R is Sorry, so this X could be the encrypted message C. Okay? So it can be anything, actually. So it can be anything, but let's say Eve uses the information she got. So she got the information that Bob sent, which is encrypted and no sense, but she can just take powers and powers and so on. So she's not gonna have the full list of these powers, but she can just manage to make a function in some sense in a classical computer to make a powers and find out what the modulo of that power is. And she knows that this is periodic because if she knows that this Bob and Alice are using RSA encryption, that they're using the private and public keys, and this C, whatever that is, when R is equals to DE, then it has to be equals to 1 modulo mu, right? So after DE, which is very large, supposedly very large, so that's why I said when Alice preparing E, it shouldn't be small number. But anyway, so if Eve tried these powers many times, then if it gets to DE, although it doesn't know what DE is, but at one point it becomes 1, then now Alice, so Eve knows that this the period, the DE is the period, the large period, at least there is some, so the Eve wants to find the period. So I'm just circulating the words, same words again, but anyway, so we know that it's periodic, but at least because there's one period here. So let's say Eve found a period, let's say R. I used R, so let's say R. So since we know that this C to the power of DE, whatever the C is, it has to be 1, so DE must be the largest, so kind of the largest period that we can think of, right? So if there is an actual period, which means that we have a period, that means we supposedly be the smallest length of the periodic table, right? So DE is kind of a multiple of these smallest period. So let's say E found a period. It could be smallest or small, in between smallest and DE. But anyway, this R must divide DE, right? So what does that mean? So since she found out the R, so she can factor it out, and R is now a factor of E1 and so on, EF, like this, right? So and then I know that this is factor of DE, and DE, what is it? It's modulo 1, modulo n. So let me go back to here. Oh, sorry. So we can argue like this, but this is actually not better. So not better than this one. So it's periodic because, let's see, it's periodic because you know that this p minus 1, 2 minus 1 is equal to modulo mu. So that's better. So whatever the C is, when you take the power of p minus 1 or power of q minus 1, so actually what I said before is wrong because DE is modulo 1, but not the power of DE is actually C, sorry. So I made a mistake here. So anyway, so we have this, so therefore the period, whatever the period of f is really, has to be the factor of p minus 1 times q minus 1. period. So when E found the period R, then R must be by P minus 1 times Q minus 1. Right? So means that if R has a factor, now Eve knows what the factor is because she knows what the number is, then these factor must be the factor of P minus 1 and Q minus 1, either of these two. Right? So she now wants to get the information, what's the factors of P minus 1 or Q minus 1. She doesn't know definitely what factor the P minus 1 is and Q minus 1 is, but she can try out whether this is right or that is right. And then every time she finds a new period, let's say like she could find the period definitely, but she could find another period. Let's say the next period, R prime, she found that there is E1 squared inside of the factor. So in this case, so this Eve can say that E1 is a factor of P minus 1 and Q minus 1. Then next time, oh, the square is here. So she can say there are 4 possible ways. So she has 3 possible ways. E1 squared is a factor of P minus 1 or Q minus 1, or E1 is a factor of P minus 1 and Q minus 1. Right? She has a kind of combinations of possibility to find out what P minus 1, Q minus 1s are factored about. So by doing this, we can find, or by combination, the factorization P minus 1 and Q minus 1, right? And thus, so when does she stop? So when she finds out that the factoring of P minus 1 and Q minus 1 indeed gives the prime P and Q. So let's say I assume that this P minus 1 is 2 times 3. Okay. And then just add 1 to 2 times 3, which is 7. Okay, that's a prime. Now I found P. If she do the same thing for the Q minus 1, then she found the Q, and then she finds the Q is also prime, then she knows that what P and Q is. So easy to find whether a single number is prime or not. But it's a thing that you cannot know what prime, so what number, the given number is a factorization of what kind of primes that is. So Eve can stop there. Once you know what P and Q is, then she can decrypt the message then from Bob. So here again, so Shor's algorithm is actually RSA code breaking algorithm, right? So for a long time they thought the RSA is kind of safe, but Shor's algorithm gave a way to think that this RSA is not safe if there is a quantum computer large enough where the number of qubits are large enough so that they can use it to break RSA code. Of course, there is no such quantum computer yet, because at least you need 1,000 or 500 qubits in a quantum computer. When you hear a news that some company made a quantum computer of a qubit number 510,000, 1,000 or 2,000, it's not about universal quantum computer, it's about quantum annealer. It's different. Quantum annealer could have a different number of qubits because it works differently. But there's no quantum computer, universal quantum computer. I think at most 30, I think, 20, maybe. So even though in that case it's not working, you cannot implement the Shor's algorithm, that kind of complicated quantum circuit cannot be implemented. So there's no practical quantum computer yet, but they got a possibility that this encryption or decryption could be broken in near future. So since then they are caring about
what other encryption and decryption could be possible. Even back then, they were thinking about what kind of encryption method is secure even by the quantum algorithm. So it's a quantum proof encryption or decryption. And anyone heard about the NIST, NIST, the challenge? Anyone heard about the challenge that asks for the new quantum, new encryption method that is quantum safe? So I think there were several rounds that they rule out this is safe, this is not safe, and so on. And then they eventually, after the third round, they eventually selected few methods that is quantum safe, which means that it's also safe in the sense of classical computing, and also it's safe whenever, even though the quantum computer is available, they are not breakable, easily breakable. So you see why the Shor's algorithm is fitting in. So it's the quantum algorithm, Shor's algorithm is actually for Eve, eavesdropper. Eve wants to use the Shor's algorithm to break the RC encryption. Because Eve wants to find a period. And what did we say about the Shor's algorithm? It's actually period finding algorithm. So the question is, now I said Eve needs a function. So if it's a classical computer, you can easily find this, make this function. But the question is, Eve has to implement this function into an oracle of a quantum algorithm in the Shor's algorithm. Right? So it's not an easy task too, but it's still possible. It's just about the possibility. So Eve knows how to make a function f into a quantum oracle in the Shor's algorithm, and if there is a quantum computer, actual quantum computer that has a large enough qubits that can implement this code breaking, then every RSA code can be broken easily. Because every time you just run the Shor's algorithm, you find a period, right? I mean, at least it's again, so I think I put it in the midterm. So the Shor's algorithm not definitely finds a period. So it's kind of a 40% chance, right, to find a period, but the rest of the probability is that you may not have a period, right? But the 40% is high enough, so you can have some kind of a combination to test out whether this is the right one and the wrong one and so on. Every time you do it, then there is a mixture of the right period and the wrong period, but you still have the chance, you still have a candidate test out whether that period is a factor of the number that you want to find. All right.